Okay, I'm hearing there's some confusion on your homework, so here's an attempt to help you out a bit. Let's go do a quick flashback to Friday's class when we were talking about the pattern we were looking at. The stairs pattern was modeling, if you looked at the numbers we're adding, the sum of the first n integers. So for instance, in our first figure, we just had 1 square. In our second figure, then we had 1 plus 2. And we talked about different ways of seeing that pattern growing. So one way was to just look at it as a column was being added to the left. And then in the third figure, so up here at the top, I'm showing my figure numbers. That's not the sum of the squares, that's the figure numbers. In the third figure, well, then I had that same figure. Whoops. Give me a second to erase. Okay, I had that same as figure 2, so I had 1 plus 2, and then I had another column. Or some of you saw it as there was an extra diagonal here, that you're adding a 1, 2, third diagonal, 1 diagonal, 2 diagonals. But no matter how you looked at it growing, the total for the number of blocks we had was 1, 1 plus 2, 1 plus 2 plus 3, or maybe it makes more sense in terms of how I just did it if I show you this way, matching up with the corresponding column. And then when we got to, eventually, we talked about the case of, well, the 10th and the 100th case, but when we talked about the 10th case, we had 10 in this column, and I'm out of room on my screen, but 10 in that column. And a lot of you, to figure out how many we had in that case, went to your calculator and did 10 plus 9 plus 8, all the way until you had done the sum of the first 10 integers. So sometimes when we look at a pattern, it's easier to see it growing in order to come up with a generalization of what's happening. And that's what we started to get to at the end of class. I put a PDF in the classwork for Friday. If you go to the Schoology calendar, there's a PDF of kind of some results that I saw throughout the day, not necessarily all from your class, where we generalize that. So this will help you with number 2 on your homework, getting back to how do we generalize it. One strategy I really liked was dividing the square into, thinking of it as a square and thinking of it as I have half the square, which would be 3 squared divided by 2, plus I have those extra triangles, which is the number of squares I have on the diagonal, but only half of them. If I generalize that, for my 10th one, it's going to be 10 squared divided by 2 plus 10 divided by 2. Hopefully you can work out that picture in your head. And for a generalization, n squared divided by 2 plus n divided by 2. There's another one involving rectangles, and I would encourage you to look at that PDF to help you out with visualizing that, and maybe it'd help you with the next one. I want to do another page. Give me a second. What? Okay, I'm not sure if this is going to be a second video or part of the same first video, but I'm moving on to your worksheet 2B, question 3, where it says, I want you to use inductive reasoning to determine the sum of the first n odd positive integers. Show numeric and visual representation of your answer. So I would encourage you to start with the visual of how do I actually picture the sum of the first n odd positive integers. Well, I've got to start with the first odd positive integer is 1. So if this is my n row up here, one odd positive integer looks like this. If I have 2 odd positive integers, well, that'd be 1 and then 3. So the sum would be 1 plus 3, but I'm worried about just visualizing it right now. So we could do a column next to it like we did with our n even integers, or we could do, whoops, let's go that back. We could do a row underneath it, just another idea, except I need 3 of them. And then if I have the first 3 odd positive integers, that would be 1 plus 3 plus 5, etc. So you can start to picture what the sum of the first n odd positive integers look like. But that's just one way of visualizing it. So why don't we try a different way of visualizing it? So let's start with this one. just there. And then for the first two odd positive integers, I'm going to keep my 1, but I'm going to build my 3. Instead of doing this and doing a row down here, I'm going to build it around my first one. I'm going to do it as kind of like a corner. So I'm going to make it look like this. So again, instead of doing this as my next odd positive integers, I'm going to do it this way. So I now have a 2 by 2 square. Maybe that's interesting to you. Maybe that's not. Sorry, I know it's a little sloppy. Let's see what the next one would look like. So the next one, I would have 3. I'm taking my previous figure, which is already 1, plus 3, and I'm adding 5 to it. Well, can I do the same thing? Instead of adding 5 as a row down here, can I actually add 5 around my figure? 1, 2, 3 in the corner, 4, 5. Sure enough. And I still created a square. That's interesting. What happens? Can you visualize what would happen if you had the 10th figure? Could you picture what that would look like? And then can you figure out how many there are? So in this one, we're doing 1, 1 plus 3, 1 plus 3 plus 5. And you can get your answers that way, but look at how you're getting your answers. You have the figure number 3 and it's creating a square with how many sides. You have the figure number 2 and it's creating a square with how many sides. And that's the power of visualization. Sometimes if we can see the pattern growing, then we can say, oh, if there are n number of positive odd integers that I'm adding, I know exactly what that's going to look like without drawing out the whole thing, and I can tell you in an instant what my sum is going to be by generalizing it with some kind of formula in terms of n. So what's your formula? How are you getting from 2 to your answer of 4, 3 to your answer of whatever you get when you add up all of these? Okay? And then the numeric approach would just be writing all of that out like I've kind of started to do here. Some people like to do a table, and that's fine too. So that hopefully that helps you with that one. Okay, third question that really seemed to be stumping people was, how do I do number 4? Figure out the number of diagonals in an n-sided polygon in terms of n. So I want total diagonals. So our smallest polygon is how many sides? Yeah, you're right, 3 sides. So there's my n is 3, n could be 4, n could be 5, n could be 6. 4 sides, just draw a 4-sided figure. Doesn't have to be a square, just a 4-sided figure. 5 sides, which we call a pentagon. 6 sides, which we call a hexagon. And I want to look at how many total diagonals can I draw. So let's change colors here and start drawing and counting. I'm going to count as I go. So can I draw from this corner to either of the other corners and not retrace something that's already there? And hopefully you're saying no. The only way to get from here is that and that, and those are already sides. Same thing from this point. So the number of diagonals that I can draw for a triangle is actually 0. Okay, let's try our quadrilateral here. So I'm going to start down here and I can go across. I can't go up because that's already a side, so is that a side? Okay, so let's go to a different corner. What if I start here? That's a side. Whoop, that's a new one. Okay, so if I grab my... I'm doing green just to show you that I'm going from a different corner here. And then that's already there. Now if I go to this corner, it looks like everything's already drawn. Do you agree? So I'm not going to recount that blue one that's already there. And then the same thing down here, everything's already drawn. So the number of diagonals that I can draw there is 2. I'm going to do one more and then let you kind of take this one away and see what happens. So let's start with this corner right here because that looks fun. So I'm drawing up to, well, let's try for a straight line. Wow. So those are my 2 diagonals I get. I can't do the sides from that corner. Then let's go to my next corner. And from here, I'm going across and down. So I've got 2 blue, 2 green. Again, I'm not trying to skip any. This one doesn't count because that's a side, and that one doesn't count. So you can start to think about how many diagonals are you getting from a single vertex. When I have 5 sides, I'm getting 2 diagonals. When I had 4 sides, I was getting 1 diagonal from a vertex. That might help you a little bit. Think about those 2 because you can't count your sides going to these two, and then you can't count the vertex that you're on. So from 5 vertices, you get 2 diagonals. From 6, I bet you can take a guess how many diagonals you're going to get. And then I'm going to do one more here. So let's go up to this corner here. And I've already got a blue one. I don't want to retrace that. But that one hasn't been drawn yet. And then keep going. But I think as you get to your next points, those have already been drawn. Yellow, green. So I'm ending with 5 here. So I don't think that's going to finish it for you. I think you're going to have to do a little more drawing. But combination of drawing, again, our goal is to figure out how are we going to get from n being 3 to knowing that there are 0 diagonals. So if I ask you a crazy question like, in a 20-sided polygon, which we call an icosagon, how many diagonals would it be? I don't know about you, I can't even draw an icosagon. How many diagonals will there be without me having to draw it and count them all out? Okay, it's supposed to make you think a little bit. See what you can do with it.